Team Fortress 2 is a game for humans, but these are not human players. These are artificially intelligent robots, and for the first time ever, they've taught themselves one of, if not the most iconic video game mechanics of all time, rocket jump. But this video is not about glorifying machines. We are here to uncover the truth about reinforcement learning, the truth that nobody talks about. It actually sucks. In this video, we'll watch the AI tackle 5 increasingly difficult jump levels. By forcing it to try such open-ended, precise tasks, the AI's weaknesses will be exposed like you've never seen before. Most RL research is on significantly simpler tasks simulated over millions of time steps. And yet, this AI can learn to jump from scratch in 1/100th of that time without any human supervision. How? Let's start at the beginning. A rocket jump has just 3 ingredients: shoot your feet, jump, and crouch all at the same time. There's a bit more nuance to it, but that's pretty much it. Crouching and jumping both amplify the explosion knockback for a ton of mobility at the cost of just a bit of health. In TF2, it turns the soldier class from the second slowest after the heavy to arguably the most mobile class in competitive play. But for the AI, it's best to start with the absolute simplest possible scenario first, a rocket jump straight up and down. This is Frederick. He's an NPC bot controlled by a series of custom server-side mods hooked up to an AI brain running in Python. Rest assured, he doesn't use any hacks and can only work on servers set up for him, unlike those other bots. For this first vertical jump test, he'll have just 3 possible actions: jump, crouch, and fire. That's it. They can only aim straight down. Here's how it works. The AI chooses actions based on 2 main pieces of information: the state and the reward. The state is all the input data that represents the world. You can think of it like the AI's eyes. But even more important than state, the reward is what tells the bot how to improve. If the state is its eyes, reward is like the AI's bank account. It's the way we explain to it which actions are best in a language it understands: numbers. For this first test, we want it to learn how to jump as high as possible, so we'll make the reward equal to the bot's height. The higher it goes, the more reward it gets, and the AI's sole purpose in life is to accumulate as much reward as possible. It watched too many Sigma grindset TikToks. It's able to maximize the rewards using what's known as reinforcement learning algorithms. These are what make it possible for the bot to learn on its own. This is what it looks like in action. At first, the AI starts with a batch of completely random actions. Then, through an alternating process of exploration, then exploitation, it learns which actions give it the most height. This is a slow and largely inefficient process, which is why I have so many bots going at the same time. It increases both diversity and efficiency of the training. All the bot's experience goes to one central brain that learns many different actions at once. Eventually, after a few cycles, the bots figure it out, consistently getting the maximum height. Now let's apply these same principles to a real challenge: a jump map. The community has made hundreds of these to practice rocket jumping, from the basics to the absolutely insane. But what better place to start than the first level of one of the absolute all-time classics, Jump Koopa. The bots will now need both height and distance to get to the exit, so we'll give them the freedom to aim wherever they want. But this freedom comes at the cost of much slower training. Whereas the actions from the previous test had just 2 options, on or off, these aim values can be anything between the min and max. This is what's known as a continuous value, so we'll also need a continuous algorithm to replace the discrete one we've been using till now. To keep things simple, we'll use this same continuous algo for the discrete actions as well, by just rounding the output to a whole number. The bots will also need a better reward signal to help guide them to the exit. We want the reward to increase as they get closer to it, which in math terms looks something like this. So with all that finally done, let's kick off the training. Just kidding, you thought that was it? Nope. Turns out the sheer volume of data makes training impossibly slow. In my last video, where the AI trained to hit air shots, they only had to choose where to aim once per test, and it still took a few hours for a full run. Now they have twice the actions to decide, and they're doing so every 4 frames. So depending on the length of the episode, it could take several hundred times longer to complete. You see, the main advantage of machine learning is that computers run faster than humans. When they can beat humans at something, it's usually thanks to sheer brute force. When we take away that speed advantage by, say, running in a real-time game and doing the computing all single-threaded, we can see how slow the AI really is. It's getting overwhelmed by a huge volume of mostly useless data here. There's just way too much noise for the AI to figure out how to improve. It's literally robot ADHD. So let's cut it down to the bare essentials. Rockets can only be fired every 0.8 seconds, so that will be our new interval between actions, since those are the moments that matter most. And with that huge reduction in data volume, it's able to start actually making progress. And after just a few hours of training, the bots are able to beat level 1 pretty consistently. So let's move on to the next challenge, level 2. The platform here is much higher than level 1, so the bot needs not 1 but 2 well-placed rockets to get there this time. Needing 2 precise actions in a row makes this level exponentially harder than before, especially considering that the second rocket, the wall shot, requires a much more precise angle than off the ground. This level might look simple to us, but remember that the bots are basically blind. We humans innately understand 3D space, gravity, action and reaction, the passage of time, and so on, but the AI starts from zero knowledge every time. Essentially, it's a deaf, dumb, blind, stinky baby. These few numbers are its entire universe. Even with all that said, the bots started making great progress right away. Right here you can see the first Frederick figure out how to shoot off the wall to get more height, which gets more reward, which gets more and more bots doing it. But unfortunately, the success was short-lived. The bots weren't able to make any more progress, and worse yet, the longer they trained, the more progress they undid. Eventually, they forgot everything. I didn't know it at the time, but this is another flaw of reinforcement learning, another crack showing. It's inherently unstable. But really the big problem here is that the bots can't reliably stick to the wall like a human jumper could. In TF2 you can move forwards, backwards, and side to side, and these same actions also have a big impact in the air too. If the bots could move, it might help them stabilize both their rocket jumping and the training. It's about time we gave Frederick the power of movement. Thanks to the power of editing, it's already implemented and working properly. What week-long rabbit hole to overhaul the control code? I have no idea what you're talking about. Let's get training. Despite even more complexity from the added movement actions, this time the bots made it to the goal just as quickly as they did in level 1. To better show how the AI improves over time, I built a way to visualize the training process. The bots are color-coded from red, the least trained, to green, the most trained. It's basically just a series of snapshots of how the AI acts throughout the training, all played back at the same time. The next challenge, level 3, is a jump for distance, and it's also the first stage hazard we see. Any bots that touch the water will be instantly teleported back to the start. It's also worth noting that the ceiling here is quite low, which makes the level much harder than it looks, especially considering that the bots have to crouch jump and fire on the same timing, where a human player could slightly delay theirs for more distance. Let's see how the training goes this time. Again, it took only a few hours of training for the bots to make it to the other side. As you can see, they're not very worried about falling in the water. It's found the right angle to aim for maximum distance and the right direction to walk, but then just spams rockets till the timing happens to line up. This strategy is a bit crude, but you can't deny its effectiveness. This is also the least human-like behavior we've seen so far. I could add a penalty for falling in the water, but that might also slow down exploration. And it is already completing the assignment, so we'll just move on for now. All the levels so far have been pretty easy for the AI, but that's about to change. Level 4 is its first real challenge. Realistically, it needs at least 4 well-placed rockets to complete, although it is possible in 3 if they're near perfect. Again, having to do these in a row increases the difficulty exponentially, as any slight error will get worse and worse with each rocket. But this time, the spike in difficulty was massive. Unlike the other levels, the bots did not manage to beat it in the first run, nor the second, nor the third. They had the right idea, but weren't able to get much height on the wall. Each training run takes about 8 hours from start to finish, so I ran them mostly at night and would often wake up disappointed and sweaty. Sometimes it would be a week before any noticeable progress was made, but Frederick and I refused to give up. He didn't have a choice though. Sometime around here, I applied to exhibit at OpenSauce, which is basically a maker fair for a bunch of creators to get together and show off cool shit. And my cool shit got accepted, meaning I now had just 1 month to get the bots ready to exhibit. Speaking of, as I kept tweaking the settings, the runs got closer and closer to the top. I'm not going to give much detail here, but just know that this was several weeks of work on mostly small improvements. But one thing that helped a lot was rewarding the bots for their velocity towards the goal, not just their position. This helped speed things up significantly. Eventually, I noticed that the bots seemed to be sabotaging themselves on the very last wall shot, suddenly going for a much lower trajectory. I eventually realized that this was actually a flaw of my reward system. If the bots overshot the height of the platform, the reward would decrease as the distance to the goal would be increasing. To solve this, I split the reward into separate horizontal and vertical parts instead of just one straight line distance, and then reduce the penalty for overshooting in just the z-axis. Thanks to gravity, the bots are pretty much always going to have to go higher than the goal position at some point, so this reward change should work for other levels as well. So with all that done and my fingers crossed, I tried one more training run, and the result was magnificent. The AI was able to clear level 4 with no trouble at all. Or so I thought. When I tried to run it again later to replicate the results, it failed. And then it failed again, and again, and again. No matter what settings I tried, it seemed like the progress I had made was gone in an instant. Remember when I said it's inherently unstable? Yeah, this is that again. Last time, on level 2, we avoided this issue by adding movement. We didn't solve it. And now that level 4 is way harder, the exact same thing is happening. The bots would make some progress and then within a few hundred steps, completely regress. At this point, I was freaking out. I had no idea what was causing the instability, and there was only a few days left to fix it before I had to drive to OpenSauce. If I couldn't get it working in time, I wouldn't have anything to exhibit except depression. Now's probably a good time to explain what makes tuning a deep reinforcement learning system so difficult. They're not like regular code where you can just add print functions and see what's happening where. It's a black box, just a huge matrix of numbers with no context, meaning it's nearly impossible to pinpoint issues or even understand what could be going wrong. There are also tons of different settings, called hyperparameters, that dictate the specifics of how everything operates. And even ones that shouldn't have a big effect, like the random seed, can make for a massive difference in the final performance. You see, reinforcement learning is perhaps the most special of the 3 main flavors of machine learning. Unsupervised is for tasks like categorizing medical data, where there's no specific correct answer. Supervised learning, on the other hand, is telling the robots exactly what behavior they're supposed to do. And although it has the best quality, training is very labor intensive since it needs a lot of data all verified by humans. Reinforcement learning is special because it can do what supervised learning does, but autonomously, meaning it supervises itself. It doesn't need humans. Supervised learning is like teaching someone a dance. Reinforcement learning is like putting a monkey on a unicycle on a tightrope and only being able to guide it with a banana taped to a stick taped to the unicycle. It's hard to get consistent results because the monkey has a lot of freedom to fuck shit up. But that freedom also makes it way more fun to watch. I could have had the bots learn exactly what to do on each level directly from human recordings, but where's the fun in giving them the right answers? We gotta see if they can do it on their own. So I started the long, slow, painful process of improving the AI's performance. That process being trial and error, where every trial takes 8 hours and every error is invisible. In other words, an endless fucking nightmare. Until finally, a breakthrough. I realized that for the class of RL algorithm I was using, it's very important to balance the rewards so about half are negative and half are positive, so the gradient isn't skewed one way or the other. And I hadn't been doing that, or even properly normalizing my other inputs. Whoops. Turns out it was a pretty simple fix, and immediately it made a huge difference. The bots were now clearing level 4 with relative ease, and the best part is that it seemed to fix the consistency issue too. And not a moment too soon, because finally I'm on my way to OpenSauce. One of my computer drives with all of my files on it decided to randomly not work. So here I'm cloning the drive, got about 3.5 hours left. Hopefully nothing bad shows up. We're just gonna see how it goes. Just another short 18 hours or so. See you there. I didn't get much footage of the actual event, but OpenSauce was so much fun. It was basically just a weekend of talking to cool people who also like making stuff, including some big YouTubers. I had such a blast showing off the AI. Shoutouts to everyone who stopped by the booth, and I'm definitely gonna try and go again next year, so maybe I'll see you there.
AI learns to rocket jump.
Hi, Cow Palace. I love you. My voice is so cooked. It's not actually that bad, but it is pretty cooked.
It was a lot of talking. I must have showed thousands of people my project, and overwhelmingly, the number one question they had was this. What is that inside your computer? All I can tell you is that it is a white liquid. If you want to know more, check out the video I made about it. There were a lot of questions about the AI too, just not as universally as wanting to know which bodily fluid was cooling my computer. But nobody at OpenSauce has seen what I'm about to show you, because I didn't get it working in time. Level 5. And believe me when I say it is by far the hardest yet, and by even further, the most important. To beat it, the bots must learn to bounce across this low platform using a technique called pogoing. Funnily enough, this is one of the easiest levels for human players, as all you have to do is just walk off the edge, crouch, and hold down fire to pogo forever. The bots, however, had a massively difficult time understanding what to do. I ran test after test, changing all sorts of things, but after hours and hours of training, it didn't look like they managed to pogo even a single time. The bots tended to try and get as much distance as possible in one jump because it gave them a much more consistent reward than failing to pogo, and they failed to pogo pretty much every time they tried. This highlights one of the biggest issues with reinforcement learning. Even though the AI can learn to intelligently explore, if they never figure out how to take the right first step, it won't know how to improve. This is where supervised learning is better. It gives the AI a basic idea of what to do so it doesn't need to figure everything out through just trial and error. To encourage the AI to pogo, I tried giving it an extra incentive, a bonus reward, if a rocket adds any upwards force in the right area. I tried like 12 different versions, but none of them worked. The bots still weren't making any progress. The biggest challenge here seems to be this edge of the platform. The bots currently get zero information about the geometry of each level, only the direction of the goal. Until now, it hasn't been much of a problem, but mastering this dropdown is absolutely crucial to starting the pogo. So I coded a way to tell the bots how far they were from the walls, floors, and ceiling. Another week of development gone, but still no progress. Then I thought maybe it's an issue with precision. The bots can only observe and act every 0.8 seconds. Maybe the problem is that's too infrequent. Theoretically, more actions per second should give the AI more finesse, so I tried doubling the rate, and did nothing. It doubled the computation time, but didn't really do anything to improve the results. At this point, I had tried so many things, including new features and tons of different hyperparameter settings, but rerun after rerun, nothing seemed to make a difference. Then I removed the bot's ability to jump. I was starting to get desperate. They kept jumping off the platform, getting too much height to be able to pogo, almost mocking me. I figured since jump wasn't needed to beat the level, removing it couldn't hurt. Of course, it didn't help much either. But it did give me another idea. Maybe the level was to blame. So I set out to find a different pogo level, but this time one that was 100% idiot-proof. And I found the perfect one, on Jump Academy. This version is way better for a few reasons. Rockets can't explode on the starting platform, it's a shorter distance to pogo across, and most importantly, the dropdown is way shorter. On this level, it is possible to jump into a pogo, where on Kuba 5 it isn't. All of these being significant improvements, I figured the Fredericks would make some significant progress. I was wrong. There were a few problems that appeared because of the level change, but even after fixing them, the bots were just as clueless as before. As a last-ditch effort, I tried limiting the bots' aim to a much smaller range, the idea being forcing them to aim mostly downwards will provide more valuable training data, kind of like a janky supervised learning. Initially, it seemed to be working. The bots were at least trying to pogo consistently, certainly better than they were before. But they still weren't making it across, and no matter how many weeks I trained them or how many things I tweaked, it became clear that the result would remain the same: failure. Is this what fatherhood feels like? I wasn't mad, just disappointed. I raised a bunch of idiots. So I did what any good parent would do. I killed them. I killed the project, I mean. I think it's finally time I let you guys in on the truth. I never got the bots to beat the level. Why? Because reinforcement learning sucks. For reference, level 4 had been a huge challenge, but at this point I had already spent twice as long as that working on level 5. It accounted for over half of the total time for the entire project. I'm talking about months here. So I had to quit. And I think that's a good thing. A great thing, even. Failing to beat level 5 is actually the most interesting thing that could have happened. Because failure is and will always be a million times more instructive than any success. And that is why you should consider joining membership on YouTube or Patreon. With your help, I can fail faster and more spectacularly than ever before. It's the ultimate learning experience. All jokes aside, your support is what makes these videos possible. Join now and you'll also get a ton of cool perks like early video access, exclusive behind the scenes, source code access, and more. Like this post where I go into detail about all the things I couldn't fit in this video. Hit the button below or join on Patreon to get started now. Now back to the thing. So what went wrong? Why does RL suck? It essentially boils down to two things. It's dumb and it's slow. But that doesn't explain why I quit. The biggest problem with RL by far is the amount of effort it takes. And not dumb effort that can be automated by another dumb robot. It needs ingenuity. Human ingenuity. To be clear, I don't think this level's impossible for the bots. I'm sure there's a million things I didn't try that could have allowed them to succeed. Being able to compute more than one thread at a time would help a lot too. But that's exactly the problem. There's so many things it could be. Thousands of research papers with ideas about every facet of the process. Every little feature has to be implemented, verified, and comprehensively tested before you know if it actually did anything. It's overwhelming. And unless you have massive amounts of resources at your disposal, there's only one way to get RL to work, and that's to use intuition. I think that's the most damning thing about RL. In theory, it's a self-sufficient robot, but in practice, it needs human ingenuity and creativity to guide its design. Although level 5 was a fail, the project wasn't. At the beginning, I barely knew anything about reinforcement learning, and now I have a Frederick that can learn more in 10,000 steps than some algorithms can in millions. So what does all of this mean for us humans? Well, the bottom line is that reinforcement learning is good for repetitive, scalable tasks with lots of good quality data. But without just one of those things, humans are so much better at learning and generalizing, and we will be for a long time. But I still believe in the promise of RL, that one day it could achieve superhuman intelligence on its own. We're just not anywhere close right now. Our most cutting-edge algorithms still feel like caveman tools. In the grand scheme of things, we're still in the AI Stone Age. And I think that's pretty exciting. Thanks for watching. Be sure to check out these videos for more about the project, and join the Discord if you want to get involved.